When we've talked about compounds like methylamine or an alkene previously, we assumed that all of the electrons were localized. In other words, that the electrons were confined to one atom, such as a lone pair of electrons, or were shared by only two atoms, such as a sigma or a pi bond. However, in this video and the one that follows it, we'll be looking at what we call delocalized electrons. These are electrons that are shared by three or more atoms. Delocalized electrons will be present if molecules have what are known as resonance contributors. This will be possible if the atoms that are sharing electrons are close to being in the same plane. Let's look at one typical example of a molecule with delocalized electrons. This is the structure of benzene, which has the chemical formula of C6H6. When we look at the structure of benzene, we notice that it is a hexagon, but it has alternating single and double bonds. In addition, each of the carbons is sp2 hybridized, and as we've learned previously, sp2 hybrid carbons have 120-degree bond angles. When we have 6 of these in a ring with 120-degree bond angles, we get a nice flat planar hexagon. Whereas previously we learned that cyclohexane actually adopts a chair conformation to avoid angle strain. In benzene, with the alternating single and double bonds and the sp2 hybrid carbons, there is no angle strain because the sp2 hybrid 120-degree bond angles fit nicely into a hexagon. Another interesting fact to note about benzene is that even though we drew the structure with alternating single and double bonds, and we know that double bonds are typically shorter in length than single bonds, when we look at the actual benzene molecule, we notice that each carbon-carbon bond is equal in length. We can explain this by writing different resonance forms. So in one resonance form, we have the double bonds in these positions. However, there's no reason we couldn't write the double bonds in the alternating positions. These two structures, when combined together by what we call a resonance arrow, a two-headed arrow relating the two structures, indicates that the pi electrons of the double bonds are delocalized around the ring. Neither of these individual resonance forms exists to any extent in reality. Instead, each of these individual resonance forms only partially describes the structure of benzene. Because of this, benzene is sometimes written as a hexagon with a circle in the middle to indicate that the pi electrons, the electrons of the double bond, are evenly spread around the ring. Proteins are very important biological molecules, as we'll learn in later videos. One of the important aspects of proteins is their three-dimensional shape, which gives them some of their important functions. So what helps keep proteins in their three-dimensional shapes? As you'll learn later, proteins consist of long chains of 2 carbons followed by nitrogen. The carbon that is bonded to the nitrogen is also double bonded to an oxygen. This carbon-nitrogen bond is called a peptide bond. When we notice that the carbon double bonded to the oxygen is also bonded to a nitrogen that has a lone pair of electrons, we'll learn that we could write a different resonance form for this peptide bond. Because we can have multiple resonance forms for this peptide bond, it means that these atoms are maintained in essentially a planar structure. This planar structure of the peptide bond keeps the proteins in a very determined three-dimensional shape, which has important implications for their functioning as a biological molecule. Now I know you're probably thinking, this guy's having so much fun writing different resonance forms, when are we going to learn to do that? Well, that time is now. Let's go over some of the basic guidelines for drawing resonance structures. First, it's important to remember that when we draw resonance structures, only electrons move. You're never going to move any of the atoms. Second, only pi electrons and lone pairs of electrons can move. You're never going to move sigma electrons. Those sigma electrons are always going to be considered localized electrons. Third, the total number of electrons does not change. In other words, when we have different resonance forms or different resonance structures of the same molecule, they have to have the same overall net charge. So for example, in this first structure, we have a positive charge on the nitrogen and a negative charge on one of the oxygens. When we draw an alternate resonance form, we still have a positive charge on the nitrogen, but now the negative charge is on the other oxygen atom. In both of these resonance forms, the overall structure is neutral because we have one positive charge and one negative charge. The fourth rule is that electrons always move toward an sp2 hybrid atom. The reason for this is that sp3 atoms already have an established octet and cannot take more electrons. The fifth rule says that pi electrons will move toward the positive charge. In this example, we see that the pi electrons furthest to the right can either move to the left toward the middle sp2 hybrid carbon, or they could move toward the carbocation on the right. Because of this rule, the pi electrons furthest to the right will move to the right toward the carbocation. This will generate another resonance form, sometimes called another resonance contributor, which has the positive charge, the carbocation, on the third carbon from the right. Now, the pi electrons on the left will move toward the new carbocation, forming a third resonance contributor, where the carbocation is now on the second carbon from the left. Taken together, these three resonance contributors form what's called a resonance hybrid. This resonance hybrid is the best description of the real structure of this molecule, and the second, fourth, and sixth atoms from the left will all have a partial positive charge instead of a full positive charge as indicated by each of the different resonance contributors. The final rule states that, if possible, you should move electrons toward the most electronegative atom. In this case, the pi electrons from the CH2 move toward the sp2 hybridized CH and C, and the pi electrons from the carbon double bond to the oxygen move up to the oxygen, because oxygen is more electronegative than carbon. However, a corollary to this rule is that if it's not possible to move electrons toward the most electronegative atom, then it is sufficient to move electrons away from the most electronegative atom, because any movement of electrons is better than no movement, because electron delocalization makes a molecule more stable, as we'll see in a later video. When we have a molecule that has multiple resonance contributors to its structure, we can make predictions about the relative stabilities of each of the different resonance contributors. In general, the most stable contributors are those that more closely resemble the actual molecule, or in other words, they more closely resemble the resonance hybrid. As well, more electronegative atoms prefer to have either the negative charge or a partial negative charge if one exists in the resonance form. Finally, if we have a resonance form that has multiple charges, the separated charges will generally be unstable. Let's look at a few examples and make predictions about which resonance form is more stable in each case. In this first example, we have two resonance forms. The one on the left is acetic acid, which has a carbonyl group, or a carbon double bonded to an oxygen, and a hydroxyl group, or an OH group bonded to a carbon. The alternative resonance form has a double bond from the carbon to the oxygen that has the hydrogen, and there's a positive charge on that oxygen. The second oxygen in the structure has 3 lone pairs of electrons around it and a negative charge. Which of these two structures would we predict to be more stable? Since we see that the structure on the right has separated charges, that structure will be unstable. In the second example, we have the acetate ion. In this case, we have acetic acid, except it has lost the hydrogen on one of the oxygens. There's a negative charge residing on one of the oxygens and a double bond to carbon on the other oxygen. The alternative resonance form for this structure has the negative charge on the other oxygen and the double bond to the oxygen on the second oxygen. Since both of these structures have just one negative charge, no separated charges, and the negative charge is on an oxygen in either case, these two resonance forms are equally stable. In the third example, we have this structure with a carbonyl group, a carbon double bonded to an oxygen, and then we have what's called a carbanion, or a negative charge on the carbon bonded to the carbonyl carbon. Its alternative resonance form has the double bond to the carbon bonded to the carbonyl carbon, and there's 3 lone pairs of electrons and a negative charge on the oxygen. Which of these two structures would be more stable? Since in this case we have a negative charge, in one structure it's on the carbon, and in the other structure it's on the oxygen, we would predict that the structure with a negative charge on the oxygen would be more stable, since oxygen is a more electronegative atom than a carbon. When we look at resonance hybrids, we see that the resonance hybrid, the combination of all the different resonance forms, will be more stable than any individual resonance form. In addition, the greater number of stable resonance structures that a molecule has indicates that we'll have greater stability in the form of what's known as delocalization energy. This delocalization energy is the extra stability a compound gains from having delocalized electrons. As we continue to study reactions in organic chemistry, it'll be important to keep in mind this idea of delocalization energy, since it will influence the reactivity of the different molecules we'll be studying.